let us start this lecture with a thought process from Benjamin Franklin, who says a house is not a home unless it contains food and fire for the mind as well as the body, which is quite true and commensurate with the thought process of Indian scriptures. And let us recall what we learned. In the last lecture, we are trying to derive a relationship for burning velocity, and in that we invoke basically all the equations of conservation of mass, momentum and energy and species, but we looked at the basically the energy equation and mass conservation, and we have also found that momentum conservation equation need not to be taken for one dimensional steady flow, because it is a change in pressure is approximately equal to 0. And if you look at I had derived expression for energy, and that is basically rho Vx dCpt by dx is equal to kg dt square by dx square plus m dot triple dash f delta SC. This I had mentioned as equation number 6. Okay. So, later on what we did, we basically looked at the for the preheat zone. In the case of preheat zone, the reaction rate is 0. So, therefore, we neglect the reaction rate or the heat release rate, and then we applied the boundary condition, arrive at this expression, that is dt by dx ignition is equal to m dot double dash Cp by kg into T ignition minus Tu. I had given equation 11. If I have not given, you can take this as a equation number 11, right, to be consistent. Now, for the reaction zone we will have to consider. For reaction zone, as the name indicates, reaction zone means reaction will be very important and conduction also will be important. Then which term will be not important? What can be approximated? Any idea? Let us draw a temperature profile, and this is my what you call, let us say this is my T ignition, this is Tf, this is Tu, and this is basically x is equal to 0, x is equal to infinity, minus infinity, and this is my reaction rate, you can say F, right. And we know that dt by dx is equal to 0 here, and similarly dt by dx is equal to 0. These are the boundary condition what we have seen. In the reaction zone, you can see that T, and which is your reaction zone? This portion is your reaction zone, right, and this portion is your preheat zone. We have already discussed this thing, I am just repeating it. So, in the reaction zone, Tij is approximately or closer, I can say, to Tf, right. So, therefore, I can write down dt by dx is equal to 0 approximately, right. This is not exactly, and this is again an approximation. Okay. As a result, we can say that Cp by T dx rho Vx is approximately 0, right. then equation 6 becomes kg dt square by dx is equal to minus f delta SC, and we will have to basically integrate this equation, right. This I can say as equation 12. What I will do, I will just multiply it by dt by dx here, dt by dx here, right, and I will have to integrate this equation. So, I can say this is dx dx. So, therefore, I can write down here as dt by dx whole square, right, d by dx dx, and this is equal to basically what, x is equal to 0 to x is equal to infinity, right. And similarly here and that itself I can write down basically half dt by dx x is equal to 0 minus dt by dx x is equal to infinity, right. Is if you look at sorry, this will be infinity and this will be 0, and by using the boundary condition, if you look at the boundary condition is basically what is that, x is equal to 0 dt by dx at is equal to dt by dx at ignition, right, and x is equal to infinity, or I can write down here x is equal to infinity dt by dx is equal to 0, right. So, if I will use this one, x is equal to infinity, this will be 0, right, yes or no, and I will take now the right hand side. Right hand side is basically I can say that is delta SC by kg. Okay, I have taken kg from left hand side to right hand side in the equation 12, and that is triple dash f integration dt, this is basically Tiz, right, at x is equal to 0, t is equal to Tiz, and x is equal to infinity, t is equal to what, Tf, right, yes or no, make sense. And because and if you look at the whole reaction rate from this region, this is the portion of things reaction rate which is negligible. Instead of integrating from T ignition to Tf, I can write down as approximately equal to delta SC by kg Tu by Tf m dot triple dash f dt. Can I write down this? Because I am saying this is very small quantities as compared to this reaction rate. This is the major one, right. So, therefore, instead of taking from here, I can take from there. This is very important this thing you should keep in mind. Okay. Are you getting? These are negligible. So, instead of saying okay, I can take from here to there, from the Tu to the Tf or the x minus infinity to x is equal to infinity, I can say.
Why how can we say negligible area?
Because if you look at the area, right, because this area is very small, and it is, why it is so, I will come to later on, but let us also we can discuss now. That is, if you look at activation energy, right, E by RUT, we will be discussing that. Unless the temperature is having that higher, you can't have any term from that. So, therefore, this will be very small term, but however it will be finite, it is not that exactly 0, it will be approximately 0, or it is as compared to the heat release in the reaction zone is very what you call higher. In the heat release rate at the reaction zone is much higher as compared to the heat release in the preheat zone. That is the thing we have already discussed, right. So, therefore, I am saying instead of taking this T ignition to T ignition to Tf integrating, I can say that. Making sense? Okay. So, now this if you look at and keep in mind that I can cancel also this minus sign, right. Then I can say, let me tell you, this is 13, the by equation 13 becomes, right, I am just rewriting that equation, that is all. Dt by dx ignition is equal to, right, delta SC to delta SC there is a little problem, like 2 square, this will be square, okay, delta SC by kg Tu by Tf m dot triple dash f dt. So, I can write down this as dt by dx ignition, right, is equal to root over 2 delta SC by kg Tu by Tf m dot triple dash f dt, right. This is, I am saying, equation 14. Now, we have already derived this expression for temperature gradient at x is equal to 0 or ignition point, right. You can see the equation 11, right. By using equation number 11, right, in equation 14 we can get Cp by kg T ignition minus Tu is equal to root over 2 delta Sc by kg integrated Tu by Tf double dash f dt, right. So, I can say this is basically equation 15 kind of things. What we will do now, we will have to now basically invoke the continuity equation, right, because here the mass flux is there, that mass flux is equal to basically rho u SL. Why we are doing? Because we want to find out a relationship for burning velocity, that is SL, right. SL means basically burning velocity for laminar flame, laminar premixed flame. So, from equation 7, right, that is the continuity equation, we know that m double dash is equal to rho u SL, right. And we can also derive, we can also find out delta SC is approximately equal to nu plus 1 Cp Tf minus Tu, right. That I think I have given as an assignment, you can do that, it is a very simple thing, right. So, by using by substituting the above expressions in equation 15, we can get SL is basically is equal to Kg by rho u Cp Tiz minus Tu, right, root over 2 nu plus 1 Cp Tf minus Tu divided by Kg Tu Tf dt. Is it fine? Okay. Now, keep in mind, let me tell this is 16. Keep in mind that this we will have to simplify a little further also, right. I can say that I can assume that Tf, let us consider that Tf is equal to 0.75. Let us consider T ignition as 0.Tf plus 0.25 Tu. I can write down this as Tiz minus Tu is equal to 0.75 Tf plus 0.25 Tu minus Tu, which is nothing but your 0.75 Tf minus Tu, right. So, by that I can write down that Tiz minus Tu divided by Tf minus Tu is equal to 0.75 is equal to 3 by 4. This is again an approximation, because I want to relate the T ignition with the Tf and Tu, right. So, if you substitute these values in equation 16, right. So, I can say this is 17, okay, using equation 17 in equation 16, we can have SL. What I am doing in this expression, basically I am taking this term, right, into the root. What I will get is basically Kg square into rho u square Cp square, right. In place of T ignition and Tu, I will be putting basically 16 by 9 1 over, that is Tf minus Tu whole square, right, and 2 nu plus 1 Cp Tf minus Tu Kg Tu Tf m dot f dt. Now, this will cancel it out, Kg will cancel it out, Cp will cancel it out, right. So, I can write down that as SL is equal to basically Kg by rho u Cp. I can write down 32 by 9. Just hold on, I am coming. Nu plus 1, right, and rho u T u T f m dot f dt. Keep in mind that this I will be considering as a alpha. What is alpha? Thermal diffusivity. I must also tell that Kg will be evaluated at the average temperature, right, kind of things, which we will take an example and do, but Tu will be evaluated at the ambient inlet temperature, right, and Cp will be evaluated at the average temperature. I will take an example to illustrate that point, right. So, I can write down this as alpha okay. Yes, you are right. I will consider this as basically 32 by 9 alpha by rho nu plus 1, right, 1 over T f minus T u by T f f dt. Keep in mind that this I can write down as 32 by 9 alpha rho nu plus 1 m triple dash f average. So, where the triple dash f average is equal to what is that 1 by T f minus T u T f m dot triple dash f dt is equal to basically MWF AF CF N1 C oxidizer N2 e power to the RUT, right, and this is from the Arrhenius relationship. I can say this portion, the average mass consumption of fuel per unit volume is nothing but that, right. And if you look at we can get this AF is your pre-exponential factor and CF is the concentration of fuel, C oxidizer is the concentration of oxidizer, E is the activation energy, RU is the universal gas constant, T is the temperature, right. So, from this what you can get is basically SL is a function of what? What is its function? Its function of basically phi or the fuel air ratio or the right, because nu is coming na, nu is the nu na, like 1 mole of fuel is reacting with nu moles of oxidizer going to the product of nu plus 1 of product. Okay. So, therefore, the equivalence ratio comes over there and it is also a function of Tu because rho u is there, this is you can say rho u, right, rho u, and it is also a function of Pu unburnt pressure, right. Of course, in this case pressure is remaining almost constant, right, and it is also depending on the inert addition, like suppose you are replacing nitrogen with argon or helium or other things. So, these are the things which you will get from the simple expression and which we will be looking at, particularly looking at the considering the experimental data later on. And in the next lecture, I will be taking an example how to calculate the burning velocity. Thank you very much.